So picking up at example 8, it says determine if each of the following functions are continuous at the indicated value, and then it says to justify by sketching the graph. So what we just did in the warm-up is exactly what I'm going to do here. I am going to try to answer the question without sketching the graph, and then I'm going to sketch the graph afterwards just to reinforce what we came up without the graph. So it's kind of like when you're a pilot and you can't fly by sight, you can't see things. This is flying by instrumentation only. You're trusting the mechanics, the math, and you're going to get to the right conclusion, and then we'll look at the picture and see how we did. All right, so we're trying to determine if it's continuous at 1. The three-step definition says that we need to analyze the road coming in from the left, the bridge at 1, and then the road coming in from the right. That's the limit from the left, the function value, and the limit from the right. So in the warm-up, I wrote my little 3 pieces horizontally. Doesn't really matter how you write it. I'm going to stack these vertically this time. I'm going to say the limit as x approaches 1 from the left of f of 1, and then the limit as x approaches 1 from the right of f. So if you get those 3 pieces of evidence, at least the notation part, written down first, now you can come back and evaluate each of those independently. So you're going to have to come up with that on your own on tomorrow's quiz. All right, now without the graph, when we're trying to find the limit from the left-hand side of 1, which piece do we use, top or bottom? The top, because left of 1 is less than 1. So we look for the less than. Direct substitution, when you plug it in, you get 1 squared plus 2 times 1 minus 3. That comes out to be 0. All right, so tomorrow in the quiz, you'll get a check for that, having the right notation and the computation. Now for the next one, I'll color code it. F of 1, which piece do we use for f of 1? Top or bottom? The top, right? Because that's also a piece like the warm-up that has the equal sign. So you're looking for the equal sign now. And by direct substitution, you're going to get the same value of 0. So the left-sided limit and the function value are the same by definition. But now from the right-hand side of 0, which piece do we use for the right of 0? The bottom. Right of 0 is greater than 0. So by direct substitution into that piece, you get 2 times 1 minus 1, which is 0. What's the square root of 0? 0. So this equals 0. And so now you get a check for that. And not unlike the warm-up now, we can say since 0 equals 0 equals 0, you'll get a check for that. That's the mathematical justification, comma, and now you answer the question in a complete sentence. F, or f of x, is continuous, not in France, but at x equals 1. So make sure you say that, not just f is continuous. Because if you say f is just continuous, that kind of assumes over the entire domain, and we haven't checked that. We've only checked it 1. So that would get another check. So 5 checks, typically, for a problem like this. All right, now let's see if we can sketch the graph. This one's going to be kind of fun to sketch the graph of. Let me shrink this down now, since we don't need it. We need the space for the graph. And we need an x and y axis, so let's go ahead and draw that first. What's the most important x value on this graph? Well, 0 is probably the most important y value, but 1 is the most important x value. That's where it changes from quadratic to radical function. Now, this is a quadratic that opens what? Up or down? It opens up because the leading coefficient is positive. You know immediately that the y-intercept is -3. So if you want to put that on there, we will see it because 0 is to the left of 1. But I need to figure out the y value where this one stops. And so by direct substitution, we've already done that. It gets to 0. And because it's less than or equal to, it would get a solid dot. Now, I don't think this one is symmetric to the y-axis. In other words, I don't think 0, -3 is the vertex. So if you want to find one other point to help you sketch a parabola, 3 points for a parabola is typically enough. Let's just go off to the side here and factor that. That factors into x plus 3 times x minus 1. And so that means our x-intercepts are -3 and +1. Well, we already knew that 1 was one of them. The other one is at -3, -1, -2, -3. And what that does is it just helps you be a little bit more accurate with your graph. Now let's do one other point here. Every single parabola in the whole wide world has a axis of symmetry that runs right through its vertex. And the vertex is always going to be at the x-coordinate. That's the midpoint of your x-intercepts. It's always halfway between your x-intercepts. So what's the midpoint between -3 and 1? -1. To find the midpoint of a number, remember, you just find their average. You add them together and divide by 2. -3 plus 1 is -2. Divide that, you get -1. So now I know that I'm going to come down, and I don't know how low I'm going to go, but at -1 I hit a low point, and then it's going to come back up and look like that and stop right there. And that's the left side of the graph. And now we know that picking up at 1, we've already plugged in, it turns into the radical function. Well, the radical function is vertically stretched by a factor of 2, and the -1 under the radical does what to the parent function? This is what the parent function looks like. Moves it. If it were the square root of x and then the -1 were outside the radical, it would be down 1. But because it's inside with the x, it's affecting the graph horizontally, it moves it right 1. And so it picks right up out of that parabola and goes into this. And there's the graph. Okay? Finding x-intercepts of a quadratic is probably the best way to sketch the graph of the quadratic unless you put it into standard transformation form, which involves completing the square. All right, so now we could test the graph and compare it to what we came up with. Yeah, the graph is in fact continuous at 1. Okay, it makes a smooth transition from the parabola to the radical function. All right, part B. I want you, like we did in the warm-up, I want you to do this one on your own once I get you set up with the notation. We're determining the continuity at -2. So you're going to need to figure out the limit as x goes to -2 from the left of g of x. You're going to need to then figure out g of -2, and then the limit as x goes to -2 from the right-hand side of g of x. If you get in the habit of writing that out first and doing it in that sequence, you're not going to go wrong. You're going to be reinforcing a good habit. Road, bridge, road. That's what I wrote down. The road coming in from the left, the bridge is the function value, and then the road going out is the same as the road coming in from the right. So go ahead and evaluate those. Take about a minute. Do it without graphing. See what you get. All right, that's a minute. Does anyone have a conclusion? Continuous, yes or no? No? All right, let's see why. Y'all say no. The limit from the left side of -2, which piece do we use for that? Top or bottom? Top, right? Left of, again, is less than. And it doesn't matter in this case if it's equal or not. The left-sided limit is just the less than. You plug in your -2 for x, and you get 6 divided by -2, which is -3. If you were to graph it, you would then put an open circle there. But for the limit, we don't care if it's open or closed. G of -2 now is looking for the equal sign. That's the bottom piece, right? There's the equal sign. So now you plug in your -2 for x, and you get -2 squared is +4. Half of 4 is 2. 2 minus 3 is -1. Now, if we were truly concerned with determining if it's continuous or not, would we really need to even find that last piece of evidence? No, because the road from the left is not the same as the bridge. It's game over for the continuity part. But again, on the test or the quiz, I'll probably have you find all three just to help you be thorough and just to award you more points. The limit from the right of -2, for what it's worth, is the same as the function value because it's greater than or equal to, so you can just put the same one right there. So you get a check for each of those. And now we'll say, since -3 does not equal -1. And it doesn't matter which -1 you're referencing, correct? It's just either one of them. Since -3 does not equal -1, that will get a check. G is not continuous at x equals -2. And you can abbreviate continuous if you want. I know it's a long word. And you can use the at symbol instead of writing out the word AT or the letters AT. So there you go. We're done. For what it's worth, quickly sketching the graph. Is there another place where this function is not continuous? It's not continuous at the transition point. The bottom piece is a parabola, so once we get past -2, it's continuous everywhere. But 6 over x, that piece has a built-in discontinuity at what x value? If we just looked at the graph of y equals 6 over x, there would be a what at where? Vertical asymptote at 0. Do we see it on our graph, though? We're only using that graph to the left of -2, which is to the left of 0, so we're not even seeing the vertical asymptote. So we can actually say this if we want. We can say more than just at -2. We could say that g of x is continuous for all x not equal to -2. If -2 was the only place that was in question because it was the transition point, 0 didn't matter because it was not graphed on that interval, and the quadratic is continuous. This graph is continuous everywhere else. So let's quickly sketch it. Here's -2. You plug it in, you get -3, and that's an open circle. So that's going to look something like that. Because remember, 6 over x looks like this. And we're only seeing the graph from here to the left. And then we pick up with the other function at -1 with a solid dot. And that looks like this. And because the y-intercept is -3, it looks like that and then comes back up like that. So what type of discontinuity do we have at -2? A jump, yeah. We could say, additionally, g of x has a jump at x equals -2. Now, what I might ask you is, without the graph, if there is a discontinuity at -2, what type is it? How would you be able to tell from the data that you collected from these three things that there's a jump there? The y values are different on what? The limits or the function value? The function value actually doesn't matter. Yeah. Whenever your two one-sided limits, those are the roads, remember. When your two limits are different y values, regardless of what the function value is, it can exist or not exist. Whenever your two roads, your two limits are different y values, that's going to be a jump. So you can figure that out without having to graph it. Okay. That takes care of the discontinuities and piecewise function. What we've been looking at has been, or you can describe it as what we call local behavior. The local behavior in New Braunfels would be the behavior that you see in and around New Braunfels. And during the summer, it can get pretty crazy on the river, right, the local behavior. When we talk about the local behavior of a function, we're talking about behavior of the function at or near x equals 0. So relatively close to the y-axis. We call that the local behavior. And we can have all kinds of local behavior. We can have, including but not limited to, x-intercepts, y-intercepts. We can have local maximums and local minimums. Those are like vertices. This function right here, at its low point at the vertex, we call that a local minimum. So that's the local behavior, and it's arguably as interesting as local behavior in New Braunfels during the summer. But we are also interested in what's called the end behavior of a graph. And a graph at most can have two end behaviors at most. So what are we talking about when we talk about end behavior? We're talking about way over there on the right end, way over there, or way over here on the left end. So if local behavior is for relatively small values of x, the end behavior is going to be for what? Large values of x. So this is going to be as x goes to infinity on the right, or as we go to the left, it's going to be as x goes to negative infinity. That's the end behavior. And unlike local behavior, end behavior is kind of boring because it's very limited into what it can do. What are some of the things that a graph can do as it goes out, let's just say, to the right? As x goes to infinity, what are some of the things a graph can do? Well, like x squared, the y values can also go to infinity. The graph can go up forever. Or they can go down forever to negative infinity. So those are two options. That's like x squared and negative x squared. We're going to study sinusoidal functions later on in the year. So you'll see that you can also have end behavior that looks like this. This would be oscillation. Like a sine wave, it's going to oscillate between two fixed values forever and ever and ever and ever. It doesn't go up forever. It doesn't go down forever. It just kind of oscillates between two fixed values. The one that we're most interested in, though, is this. You can actually have the y values taper off. And when the y values taper off, guess what graphical feature lives there? Think about this parent function 1 over x that we already, I'm going to get there right when it's going to quit ringing. Yeah. The graph of 1 over x, the y values taper off. What graphical feature do we have that lives there? An asymptote, right? What type of asymptote? The vertical asymptote is your discontinuity. This one is a horizontal asymptote, and it is not a discontinuity. A horizontal asymptote. And I repeat, a horizontal asymptote, which you can abbreviate HA, is not a discontinuity, although it is an asymptote. A vertical asymptote is a discontinuity because we always talk about a graph from left to right on an increasing x interval. And a vertical asymptote runs north to south forever and ever and ever. And so you have to lift your pen, pencil, or finger to get on the other side of it. Whereas a horizontal asymptote, you could just draw it forever and ever and ever, going off to the right, getting closer and closer to it, and never have to lift your pen or pencil. So it's not a discontinuity, but it is an asymptote. We want to be able to figure out what the end behavior of a graph is, and if it does taper off towards an asymptote, we want to be able to figure out what that y value is. So that's what we're doing next. Bless you. These are the two limits that we're going to write and evaluate when we're analyzing end behavior, okay? These are one-sided limits by definition. The limit as x goes to positive infinity. That's a one-sided limit. You can only approach positive infinity from which side? Left or right? You can only approach positive infinity from the left-hand side. If you approach positive infinity from the right-hand side, that's going to be weird, right? How'd you get to the right of positive infinity? And the limit as x goes to negative infinity, you can only approach negative infinity from the right-hand side. So these are one-sided limits, and that is the analysis for determining end behavior. So when I ask you, describe the end behavior of this graph, show your analysis, this is what I mean. I'm looking for you to write that and that. All right, so let's try it out on example 9. Using the graph from example 5, which I forgot what it was, maybe we'll resketch it, analyze the end behavior by evaluating the two following limits. All right, sketching this by transformations. Step 1, identify the parent function. What is it? It's 1 over x, okay? The next thing we want to do is put this into standard transformation form. So I'm going to pull the 4 out of the numerator, and that leaves a 1 in the top, and I get x plus 2. So there is the standard transformation form. Now we can sketch the graph by using transformations. What does the negative do to any graph when it's multiplied in the front of the function. Like x squared versus negative x squared. Flips it across the x-axis. Let's go ahead and write that here. The negative is going to be an x-axis reflection. Some of y'all haven't had transformations in quite a while. All right? So that's going to take the graph of 1 over x and flip it across the x-axis. So now it's going to live over here in quadrants 2 and 4 instead of 1 and 3. So keep that in mind. What does the 4 do if it's multiplied out in front? It's affecting the y values. What's that? Yeah, it's a stretch. It's a vertical stretch by a factor of, which I abbreviate BFO, by a factor of 4. The y values are 4 times taller than they used to be. So that's not going to really affect the orientation. The shape is just going to be a little bit steeper. And then on the inside, what does the plus 2 do to any graph? Well, if it's added or subtracted, it's not a compression. Those are the multipliers, but it is horizontal. If it's added or subtracted, it's going to be a shift, and this one is left or right? Left, right? This moves the graph left 2 units. It's the opposite of what it immediately appears when it's on the inside. Plus 2, you might think it to the right, but it's actually to the left. Okay, so I know there's a vertical asymptote right here at negative 2, and I didn't move the graph up or down at all, so there should still be a horizontal asymptote at 0, just like the parent function had. And now it's going to live over here, because we reflected it across the x-axis, and it's going to live over here. Now, if you look at that and tell me that it's 4 times steeper than the parent function, I'll say thank you. I meant for it to be. And that'll be the same standard I use when I see your graphs. It's really hard to show those vertical stretches. It's a lot easier if you're comparing it to an original graph. So there you go. There's the graph. Now we can answer the question, what is the limit as x goes to infinity? Well, now you hop on the graph to the left of infinity, and you start heading out to the right, approaching infinity. What are we getting closer and closer to? Well, as the x values go to infinity, what are the y values approaching? They're slowly increasing, approaching 0. Yeah, so this equals 0. They're getting bigger forever and ever and ever. The graph goes up forever and ever and ever, but it doesn't go up to positive infinity. It's limited by the x-axis, which is y equals 0. It's getting closer and closer to it. This one will never touch it. And what would be the limit as x goes to negative infinity? Well, you hop on the graph and start heading out to the left. You're approaching 0 again. This time you're approaching 0 from the positive side, whereas on the other, you're approaching 0 from the negative side. So we kind of let the cat out of the bag already. What graphical feature on the graph of f causes the graph to do that? Well, there's a what? Horizontal asymptote. Now we're going to list it. A vertical asymptote is always of the form x equals, because a vertical line is of the form x equals. A horizontal asymptote is a horizontal line, and every horizontal line is of the form y equals a number. So it's going to be at y equals 0. If you just put horizontal asymptote at 0, that would be a misstatement. It's a horizontal asymptote at y equals 0. And it's affecting the graph on both ends. Now, my question to you is, did you have to sketch the graph to figure that out? Well, for the first time, yeah, maybe it was helpful. But in the future, here's what we could do. We can't plug in infinity per se for x. But let's pretend that we can. F of infinity, right? It's not a number, but if we plug it in, we get negative 4 over infinity plus 2. So let's see what that's going to equal. First of all, what is infinity plus $2? If you have infinitely many dollars and someone gives you $2 more, do you say, thanks, I needed that? No, you're like, I didn't even feel that. Infinity plus 2 is still infinity, right? Now what happens to this ratio when the top is a negative 4 and the bottom gets really, really big, really, really fast? What happens to your ratios when the denominator gets bigger faster than the numerator? Like, let's try this out, like negative 4 over 10, negative 4 over 100, negative 4 over 1,000, negative 4 over 10,000. What's happening to these ratios? Getting bigger or smaller, magnitude-wise? They're getting smaller, magnitude-wise, approaching 0. Now, because they're always going to be negative numbers, you know that this is going to be approaching 0 from the negative side. So from below. And that's exactly what our graph does right here. We're approaching 0. The magnitudes are getting smaller from the negative side. And you could do the same thing for the other side. If you try what is f of negative infinity, you plug it in, you get negative 4 over negative infinity plus 2. Oh, thank you. Perfect. Now let's look in the denominator. What's negative infinity plus 2? Is it still negative infinity? Let's say you owe somebody infinitely many dollars, right? Owing is a negative number. And you pay them back $2. Do they say, oh, we're all square now, thanks? No, you pretty much still owe them infinity many dollars. So negative infinity plus 2 is still negative infinity. Now what's a negative divided by a negative? A positive. So that's the same as 4 over infinity. And now what happens to 4 over infinity? 4 over 10, 4 over 100, 4 over 1,000, 4 over 1,000,000. What's happening to those numbers? Getting smaller and smaller and smaller, approaching 0 again. But this time they're all going to be positive numbers. So you can actually say that the limit as x goes to negative infinity is 0, and it approaches it from above. So that's the cool thing about infinity. You can just analyze how fast the numerator grows compared to the denominator. And anytime the denominator grows faster than the numerator for huge values of x, it's always going to be approaching 0. So you really don't even need the graph. Okay, so that's kind of cool. Let's go ahead now and define a horizontal asymptote. We need the limit in order to define a horizontal asymptote. And here it is. If the limit as x goes to negative infinity of a function equals L, where L is some finite y value, and or, so if both happen or just one of them happens, the limit as x goes to positive infinity equals L. Again, where L is a finite y value. Then we know that function has a horizontal asymptote, an HA, at y equals that number. So it's possible for a graph to have one horizontal asymptote and have the graph affected on both sides. We just saw that with 1 over x. It's possible for a graph to have one horizontal asymptote and only be affected on one side. But a graph can also have two horizontal asymptotes. That's the maximum number, and the graph can be affected by each one differently on either end. All right? So there's the definition of a horizontal asymptote. If either one of the end behavior limits equals a finite y value, there's a horizontal asymptote there. All right, now 2 important things to clarify about horizontal asymptotes. First of all, a horizontal asymptote is not a discontinuity, as I've already mentioned. A horizontal asymptote then can be crossed. You can actually cross a horizontal asymptote, whereas a vertical asymptote you can't cross at all. Here's an example of a graph that crosses its horizontal asymptote. Something that looks like this. If you think of a graph that oscillates above and below an x-axis, but each time it does it by less and less and less and less, kind of like when you bounce a ball on the ground, every time it bounces up, it gets smaller and smaller and smaller. What's happening to these y values as we go out to the right? What is the limit as x goes to infinity? It's 0. They're approaching 0. You can actually see that it's going to be impossible to continue drawing it above and below the x-axis. You're going to have to start drawing it as a horizontal line. But even if you zoomed in way over here, it would look just like this. Even if it continues to cross above and below forever and ever and ever, but by less and less and less, there's still going to be a limit approaching 0, which means there is a horizontal asymptote at y equals 0. So we could draw it in there like that. How many times then would this graph cross its horizontal asymptote? Infinitely many times. Yeah. So a horizontal asymptote is an asymptote, but it is not a discontinuity. Okay? It is not a discontinuity. Most graphs, to be honest, like this one that have a horizontal asymptote, most graphs don't cross their horizontal asymptote. But it is a possibility. So I want you all to be aware of that. Okay, here we go. Example 10. For each of the following functions, we're going to determine the left-end behavior, the right-end behavior, and then we're going to determine if the graph has any horizontal asymptotes. And we're going to do it without the graph. So here we go, example A. Let's go ahead and write our steps out. The limit as x goes to infinity of f of x. The limit as x goes to negative infinity of f of x. And then horizontal asymptotes. Remember, if the answer to either one of those at the top is an actual y value, we will have a horizontal asymptote. I'm going to copy this and paste it on the next couple of problems. It's kind of a nice thing to be able to do with Notability. All right, so what can you tell me about this function f of x? What is the graph going to look like? It's a parabola. How do you know? X squared. Does the parabola open up or down? Down. Good. Yes. Yes. Now, because it's a parabola that opens down, you could draw something that looks like that. The local behavior is going to be rather interesting. It can have positive x-intercepts. It can have a positive or negative y-intercept. We don't really care, though. The end behavior is very predictable. Because the parabola opens down, what's the limit as x goes to infinity and negative infinity? What are the y values doing on this graph as we go out to the right and to the left? They're going down to negative infinity. So you're going to put, as your answer to both, you're going to put negative infinity. Now again, just like with a vertical asymptote, when you say the limit is negative infinity, you're saying two things. You're saying, number one, the limit does not exist. It goes down forever. It is not limited to how low it's going to go. But then you're telling me why it doesn't exist. Because it's decreasing without bound. So, will we have any horizontal asymptotes? How do we know? Well, is negative infinity or negative infinity, are either one of those finite? Is infinity a finite number? No, it is by definition infinite. And so there will be no horizontal asymptotes. Remember, if either one of those numbers, either one of them was an actual y value, a finite number, there'll be a horizontal asymptote at y equals that. Now, what if we didn't know that this was a parabola that opened down? Is there a way to come up with negative infinity without the graph? Say yes. Yes. How then? Well, I'll show you how. With infinity or negative infinity, the thing that's going to contribute to the majority of the growth for huge, unfathomably large values of x is the leading term. And what makes the leading term the leading term? The fact that it's in front? No, the fact that it has the largest exponent. Now, all of this other stuff behind the leading term, 5x minus 1, that'll affect the graph locally for small values of x. But for huge values of x, that is so small compared to what the leading term will do that it's effectively zero. You can neglect it. And all you have to do is analyze what's happening to the leading term. So let's try it out. If you want to know what's happening as you approach positive infinity, plug a positive infinity into the leading term. Negative 3 times infinity squared. Well, let's evaluate it. What's infinity squared? Infinity. Good. Now, what's infinity times negative 3? What's a positive times a negative? A negative. So it's negative infinity, and that's the answer for the right-end behavior. If you want to know what the left-end behavior is, go ahead and just analyze the leading term. Negative 3 times negative infinity squared. What is negative infinity squared? Positive infinity. And what's positive infinity times negative 3? Negative infinity, and that's the answer to the left-end behavior. So because it's infinity, and only because it's infinity, you can forget about anything that's not the leading term. The growth of this function is going to be dominated by the leading term exclusively, okay? You can't do that if you're evaluating it, let's say, at 5, okay? Because now the x value is so small, everything contributes. All right? So let's do this one that way then. Let's go ahead and just, if you copied and pasted, oops, I always paste the image. If you update, you get to paste things as images now, which means you don't have to, it won't erase it. It's pretty cool. All right, so maybe we know what the graph of 4x cubed minus 2 looks like, but let's pretend we don't. What would be the limit as x goes to infinity? Well, that's the right-hand behavior. Which term is going to do most of the contributing to the growth? The first or the second term? The first, right? So sorry, -2, you're kind of meaningless in terms of the end behavior. So what do you get when you plug in a positive infinity? What is 4 times positive infinity cubed? Positive infinity, right? Huge cubed is huger, and huger times 4 is huger, which is infinity. Okay, positive huger. And what do you get when you plug in a negative infinity? What's negative huge cubed? Negative huger, or negative infinity. And what's negative infinity times positive 4? Negative infinity. So that's how you could do it without knowing what the graph looks like. Now, will we have a horizontal asymptote? No, because both of those are infinite. We have no horizontal asymptote, none. Now, just to kind of talk about what this graph looks like, the parent function is what I call the disco graph. Looks like John Travolta on the cover of Saturday Night Fever. Okay, if I were standing, I'd show it to you. What does the 4 do to that graph? Vertically stretches it by a factor of 4. So that's going to effectively make the graph a little bit steeper like that. And what would the -2 do to that graph then? Well, it's outside the cube, so it's going to be a vertical shift down 2 units. So that comes down 2 units, and this comes down 2 units. And so the green graph is what it looks like. So now you can really confirm. As you go out to the right forever, the y values go up forever. And as you go out to the left, the y values go down forever. But you don't need the graph when you're analyzing end behavior. All right, let's copy and paste this one. Doing the same thing, what would be the limit as x goes to infinity? Well, what do you get when you plug in an infinity? What's infinity minus 5? Infinity. And what's the square root of infinity? Infinity. And what's infinity times 2? Infinity. So there's the right-hand behavior. Now for the left-hand behavior. Plug in a negative infinity for x. What's negative infinity minus 5? Negative infinity. What is the square root of negative infinity? Can we take the square root of any negative number? No. So it doesn't exist. This would be DNE. Now things can fail to exist for many, many, many reasons. This is not DNE like the first one is DNE. Remember, when you say that the limit is infinity, you're saying that the limit doesn't exist because the y values are going up forever and ever and ever. On the second one, you have to say DNE because the reason it doesn't exist is because the graph doesn't exist there. The y values aren't doing anything because they're not there. Do we have a horizontal asymptote? Are either one of these finite y values? No, so there's none. Now to think about what the graph looks like, the parent function is of course the radical x function. And the 2 is going to vertically stretch it by a factor of 2. So it's now going to be a little bit steeper. And the -5 moves that graph to the right 5 units. So here's what the graph looks like in red. And you can clearly see now as you go out to the right, the y values go up, 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 up. Kind of at a decreasing rate, but they'll go to infinity. And what is the left-end behavior? Well, we don't even have the graph living anywhere to the left of 5. So there is no left-end behavior, which now makes an important distinction. When we talk about the left-end behavior of the graph, we're not talking about the leftmost part of the graph. The leftmost part of the graph would be at 5, 0. When we talk about the left-end behavior, we're talking about as x goes to negative infinity. And this graph has none. Okay? Let's see if we can finish these up very quickly. What would be the limit as x goes to infinity on this one? Well, now we have a ratio again. So I got to look at the leading terms in the top and the bottom. So I look at the 3x and the 5x squared. The +1 and the -2 for huge values of x, practically insignificant. Now, which one grows faster for huge values of x? X to the first or x squared? X squared. So what's happening to your ratios when the denominator gets bigger faster than the numerator? It gets smaller and smaller, approaching what? 0. So the limit as you go out to the right is going to be 0. The limit as you go out to the left is also going to be 0. It might just be approaching 0 from a positive or negative side. You could figure that out by plugging in that positive or negative number. So do we have a horizontal asymptote? Yes, at y equals 0. Cool. Let's go to the next one. We look for the leading term in the top. What's the leading term in the top? Good. It's not in the front. It's at the back. And then the leading term in the bottom is 3x squared. Everything else then is practically 0. Now, which one's going faster, x squared or x squared? They're pretty much growing at the exact same rate. In other words, if you looked at the leading terms, 4x squared over 3x squared, what would happen to the x squareds? They would divide out, and what are you left with? 4/3. That, believe it or not, is the end behavior limit. Everything else is practically 0, and because they're going to the same type of infinity, infinity squared over infinity squared, they're going to divide each other out, and you're just left with the leading coefficient over the leading coefficient. Do we have a horizontal asymptote then? Yes, at y equals 4/3. Now, I don't think we're going to have time for the last one, so we'll just stop right there at 10e, and we'll pick up with 10f tomorrow. We'll finish tomorrow pretty easily. We'll quiz tomorrow over what we've done so far, and then we'll finish the notes on the worksheet that we do on Thursday, okay? Have a great rest of the day.